Chevyshev's theorem applies to any distribution, no matter what the shape is. For the empirical rule, you must be told that you've got bell-shaped data, or they might say normal, or they might say mound shape, but anything in that shape. All right, and what it says is that approximately 68% of the data values will fall within one standard deviation. Approximately 95% of the data values will fall within two standard deviations, and approximately 99.7% of the data values will fall within three. So that looks like this. So if you've got your mean here in the middle, and plus or minus one standard deviations here, 68%, plus or minus two standard deviations, 95%, and then here, three standard deviations, 99.7. So let's do one example. So suppose that the scores on National Achievement Exam have a mean of 480 and a standard deviation of 90. If these scores are normally distributive, that's good enough right there, then approximately 68% of the data values will be between what two numbers? So if scores are normally distributed, that tells me I have normal data, mound, so bell-shaped, I could say bell-shaped. So 68% corresponded to how many standard deviations? One standard deviation, right? So that would be mu plus or minus one standard deviation, which would be 480 plus or minus 90, and that would be 390 on the low end up to 570 on the upper end. And they also wanted me to find 95%. 95% corresponded to two standard deviations. So that would be 480 plus or minus 2 times 90. And that's 480 plus or minus 180. So that gave me a lower end of 300 and an upper end of 660. Remember, empirical rule, you have to know you have normally shaped data.